K218b may be sending humanity one of the most unusual signals we've ever detected. When scientists took a closer look at this distant world, they made a bold suggestion. Earth might not be the only place in the universe capable of supporting life. But what actually makes a planet habitable? It's not just about being the right distance from its star. Many factors matter. Its chemical composition, atmosphere, nearby celestial bodies, and even how stable its star is. In simple terms, a habitable planet must be able to maintain the basic conditions needed for life over long periods of time. That includes liquid water, a reliable energy source, and the essential chemical building blocks of life. Earth is special because it sits in the sun's habitable zone, where liquid water can exist on the surface. But being in that zone doesn't guarantee life. A planet could have the right temperature, yet still be blasted by intense radiation, making it completely hostile. And that brings us back to K218b, a planet that has been making headlines in recent years because it might have something we've been searching for all along. K218b is an exoplanet, a world that exists beyond our solar system. Most planets orbit a star, although there are rare exceptions, like rogue planets drifting through interstellar space. K218b orbits a red dwarf star called K218. This star is extremely dim, far too faint to be seen with the naked eye. The planet itself is about 124 light-years away from Earth. It belongs to a class known as sub-Neptunes, meaning it's smaller than Neptune, but still much larger than Earth. Its radius is about 2.6 times that of Earth, and its mass is roughly 8 times greater. K218b completes one orbit around its star in just 33 days. Interestingly, the amount of energy it receives from its star is similar to what Earth gets from the sun. Its equilibrium temperature is estimated to be slightly below freezing, but this doesn't mean you would actually feel that temperature on its surface. Equilibrium temperature is only a theoretical value. It assumes the planet simply absorbs and radiates energy without considering the effects of its atmosphere. So what would the real temperature on K218b be like? It's hard to say. The actual surface temperature depends heavily on its atmosphere, how thick it is, what it's made of, and how it traps heat. In other words, it could be much warmer than the simple estimates suggest. But what truly made K218b explode into the spotlight isn't its size, it's what might be in its atmosphere. In 2019, scientists announced the detection of water vapor in its atmosphere, instantly making it a major target for further study. Then, in 2023, the James Webb Space Telescope detected methane and carbon dioxide, both carbon-based molecules. And here's where things get really interesting. Researchers also reported a possible detection of dimethyl sulfide, or DMS. It might sound unfamiliar, but on Earth, DMS has a very special origin. It is primarily produced by marine microorganisms, like phytoplankton. So if this molecule truly exists in the atmosphere of a distant planet, scientists get excited, because it could hint at some form of lifelike activity. On Earth, DMS is strongly linked to biological processes, and that's exactly why this discovery matters so much. DMS isn't just a byproduct of life. It also plays a role in sulfur cycles and can even influence cloud formation and climate. That's why, if it's detected on another planet, it's considered a potential biosignature. But here's the problem. No one can prove that the DMS on K218b, if it's really there, comes from life. The signal is still weak, and scientists are actively debating whether it truly exists at all. And even if it does, it doesn't automatically mean there's life. Laboratory experiments have shown that under certain non-biological conditions, DMS can also be produced. In fact, similar molecules have been found in comets and interstellar clouds, places where oceans full of microorganisms clearly don't exist. So what makes K218b so fascinating isn't that we've already discovered alien life. It's that this planet sits at a very delicate boundary. Either we're seeing the first subtle hints of life beyond Earth, or we're witnessing a type of planetary chemistry we've never fully understood before. And honestly, either outcome would be groundbreaking. But what K218b is actually like is still far from settled. Some researchers think it could be a Hycean world, a planet with a hydrogen-rich atmosphere and a vast ocean covering its surface. Others argue it may be more like a mini Neptune, wrapped in a thick, heavy atmosphere with no true liquid ocean suitable for life below. There's even a possibility that its surface isn't water at all, but something far more extreme, like a global ocean of molten material. And that's exactly why size and mass alone can't tell us whether a planet is truly habitable. Observations from both the Hubble and James Webb Space Telescopes suggest that K218b's atmosphere is rich in hydrogen. Water vapor was proposed earlier, but more recent data indicates its abundance may be relatively low. Ammonia hasn't been clearly detected, while methane and carbon dioxide are now more firmly confirmed. As for what the planet actually looks like, whether it has clouds, oceans, or even a clear boundary between sky and surface, we simply don't know yet. For now, it all comes down to models and simulations. Some suggest that if the atmosphere is thick enough, it could trap heat and create conditions very different from what we expect. The boundary between ocean and sky on K218b might not even be clear. Some models suggest the transition could be blurred, almost seamless. Others propose that its upper atmosphere may contain a temperature inversion, similar to a stratosphere, where temperatures actually increase with altitude. In simple terms, the most honest answer right now is this: K2-18b is incredibly promising, but we are still far from any final conclusion. For now, scientists can only keep collecting more data, hoping these signals become clearer over time. With enough observations, we may eventually understand whether we're seeing complex chemistry or something that truly resembles life. And the excitement around K2-18b isn't just about this one planet. In recent years, scientists have begun noticing several intriguing signs that life might be more common in the universe than we once thought. The first clue comes from planets like K2-18b, where potentially life-related gases appear in distant atmospheres. The second clue comes from a young, forming star called V883 Orionis, located about 1,300 light-years away from Earth. Surrounding this young star, V883 Orionis is a Vishal disk of gas and dust, and within that disk, astronomers have detected 17 complex organic molecules, including some that are linked to the precursors of DNA and RNA. What does that mean? It suggests that even before a planet fully forms, some of the chemical ingredients for life may already be present, and that's a big deal. For a long time, many scientists believed these complex molecules could only form later, after a planet cooled down and developed oceans. Others thought they might have been delivered by comets or asteroids over time. But these new observations point to a different possibility. The building blocks of life may not be assembled later. They could be there from the very beginning, mixed into the gas and dust as a star system forms. In other words, life might not be the result of a long chain of rare accidents. Instead, many star systems could be born already carrying the seeds of life chemistry. And the third clue is even more radical. Some researchers now suggest that life might not even require a star at all. In the past, when we talked about habitable zones, we assumed life had to exist near a star, at just the right distance. Too close, and oceans would boil. Too far, and everything would freeze. But new models are challenging that idea. They suggest that in extremely cold, dark, underground environments, life might not depend on sunlight at all. It sounds counterintuitive. After all, high-energy cosmic radiation is usually seen as dangerous. It damages DNA and disrupts electronics. But under the right conditions, it could also become a source of energy. When cosmic rays strike underground ice, they can break apart water molecules, producing hydrogen, oxygen, and other highly reactive chemicals. In theory, these could provide energy for simple microbial life. This idea has led to a new concept: radiolytic habitable zones, places where the primary energy source for life isn't sunlight, but radiation. Following this line of thinking, scientists have started to look beneath the surface of planets like Mars, because even in a frozen, lifeless landscape above, there might be hidden environments below, quiet, dark, and just possibly alive. Beneath the icy crust of Europa, inside the hidden oceans of Enceladus, and even deep within rogue planets that drift without any star, there may exist environments capable of supporting extremely primitive life. In fact, some simulations suggest that Enceladus could be one of the most promising candidates for this kind of radiation or chemistry-driven ecosystem. And this leads to a truly disruptive idea. If life doesn't require sunlight, doesn't need warmth, and might not even need a star at all, then the number of places in the universe where life could exist suddenly increases dramatically. Of course, we're most likely talking about very simple life. Without sunlight, there's no photosynthesis. Without a stable, high-energy input, it's hard to sustain complex ecosystems. So complex life, like plants and animals, probably still depends heavily on stars. But the simplest forms of life, they may not be nearly as picky as we once thought. And Earth itself gives us a clue. Some of the oldest and toughest life forms on our planet live in the most extreme, lightless places, near deep-sea hydrothermal vents, beneath thick ice, or deep inside caves. They don't rely on sunlight, but on chemical reactions in their environment, which raises a fascinating possibility. What if the most common form of life in the universe isn't something like trees or animals, but something far smaller, hidden, and almost invisible, waiting in the dark? Not animals, not civilizations, but microscopic life, hidden underground, or deep beneath alien oceans. That wouldn't be surprising at all. When you connect all these clues, a bigger picture begins to emerge. It's not that aliens have already revealed themselves. It's something far more profound. The threshold for life may be much lower than we once believed, and the environments where life can exist may be far broader than we ever imagined. It might drift in the atmospheres of distant planets like K218b, or form within the dusty disks around young stars like V883 Orionis, or lie buried beneath ice, surviving on radiation and chemical reactions. If all of this turns out to be true, then what changes isn't just the fate of one or two planets, it's our entire understanding of the universe. Life may not be a rare exception. It could be far more resilient and far more common than we ever imagined. And yet, even today, the only world where we can confirm life exists is Earth. But maybe that's exactly why we keep looking, fixated on those distant worlds, searching for even the faintest sign. So far, we've discovered thousands of exoplanets, and each one could be hiding a story we've only just begun to understand. Among the thousands of exoplanets we've discovered, some may even offer conditions more favorable for life than Earth. Scientists sometimes call them superhabitable worlds. And interestingly, many of these planets orbit red dwarf stars, small, dim stars that are far more stable and long-lived than our Sun. Our Sun has only a few billion years left, but red dwarfs can remain stable for tens to hundreds of billions of years. That means planets around them have far more time for life to emerge and evolve. In ideal models, a truly superhabitable planet might have a slightly thicker atmosphere, better at retaining heat and protecting life. It could be a bit warmer than Earth, with a more balanced mix of oceans and land, and it would orbit a long-lived, relatively calm star. Some well-known candidates include Proxima Centauri b, TRAPPIST-1e, and LHS 1140b. Some of these worlds are relatively close, some are likely rocky, and a few may even have thick atmospheres and abundant water. That's why they've become some of the most important targets in the search for life beyond Earth. But the limitations are just as clear. For most of these worlds, all we really know are their size, their orbit, and an estimate of their temperature. Whether they truly have atmospheres, oceans, or stable surface conditions, we're still far from seeing clearly. At the end of the day, we haven't found extraterrestrial life, not yet, and we don't have a single exoplanet confirmed to be inhabited. But something has started to change. In the past, we only knew that planets existed beyond our solar system. Now, we're beginning to detect what gases exist in their atmospheres, like on K218b. We're identifying complex organic molecules around young stars like V883 Orionis. And we're realizing that even frozen worlds, hidden beneath ice, might sustain chemistry driven by radiation. For the first time, humanity is no longer just asking, is there life out there? We're starting to ask deeper questions. Which kinds of worlds are most likely to host life? What forms might that life take? How similar or how different could it be from life on Earth? And maybe the final answer won't be a simple yes or no. Maybe it will be something far more surprising. That life in the universe doesn't follow just one rule, but many, and we've only just begun to understand them. It may not be alien civilizations flying starships like in the movies, but just an unusual spectrum, a rare molecule, or a faint metabolic signal beneath alien ice. But the moment that's confirmed, Earth will lose its status as the only known world with life. I'm South. See you in the next universe.